A safe landing thanks to the cushioning provided by Oleo type units built into the landing gear of this aircraft. A common practice now in large and small aircraft. Peter Thornhill, the founder of Oleo, hit upon the novel idea of separating the gas and oil in the Oleo strut with a floating piston. This enabled the strut to work at any angle, even inverted. The Oleo industrial hydraulic buffer was developed from this earlier Oleo aircraft strut technology. Oleo International are specialists in the design and manufacture of hydraulic buffers. They are leaders in the field with over 60 years' experience in solving impact problems in the rail, elevator and industrial business sectors. What sets the Oleo hydraulic system above all other mechanical buffers, such as springs and elastomers, are their ability to absorb and dissipate at least 95% of the impact energy. This is much higher than any non-hydraulic system, resulting in considerable savings on wear and tear costs, as will be demonstrated. The welcome reduction in gearbox repairs on this crane after installing Oleo buffers is a good example. The secret of a good buffer is to dissipate the energy of impact in a way other than returning that energy as recoil back to the object striking it. This is the major drawback of most mechanical buffers. It is recoil shock that shakes your bones and does all the damage to moving machinery parts, especially drive chains such as gearboxes. The hydraulic system transfers most of the impact energy into heat in the oil, which dissipates through the cylinder casing into the atmosphere. The compressed nitrogen gas provides a low recoil force merely to re-extend the plunger and reverse the oil flow after the impacting load is removed. This demonstration rig illustrates the smooth and recoil-free action of the Oleo hydraulic buffer's energy dissipation principle. A 350-pound load free falls 3 feet, striking at a speed of 850 feet per minute, with an impact force of approximately 4 tons. Not a drop is spilt thanks to the Oleo Type 21 buffer with the 50mm stroke used here. But how do these Oleo buffers work? The fundamental principle is that the resisting force of the hydraulic buffer is proportional to the velocity of the impacting object, and not the stroke, as is the case with spring and rubber buffers. The resisting force results from forcing a liquid, oil in this case, through a control orifice. The size of the orifice determines the resistance. These cutaway models show the various components of the buffer. The impacting mass strikes the buffer head, which is attached to the plunger. This fits into the cylinder, which in turn is solidly mounted on a support structure suitable to the application. Centrally bolted to the cylinder is the metered pin, which controls the size of the orifice in the centre of the plunger's piston, and through which the oil in the cylinder chamber is forced into the plunger chamber. This is the floating separator piston, which keeps the nitrogen gas on this side separated from the oil on this side. Let's watch the buffer in its step-by-step operation. The mass impacts the buffer head. As the plunger is depressed, oil is forced through the piston orifice. At the beginning, the velocity is greatest, so the orifice is at its maximum size at the thin end of the metering pin. As the velocity diminishes, the orifice size in the piston is decreased as the increasing diameter of the pin moves through the piston, thus maintaining the resisting force in a controlled, pre-designed manner for each application. No periodic adjustments are needed after installation. The metering pin design in fact delivers a fixed pattern of resistance at the same time the oil entering the plunger chamber compresses the nitrogen gas via the floating separator piston. When the impacting object moves away from the buffer head, the nitrogen gas expands and using a very low force restores the plunger to its fully extended position. It reverses the oil flow back to the cylinder and readies the buffer for the next impact. Therefore, there is virtually no recoil force imparted back to the striking object. This means there's very little shock to your expensive machinery, putting money in your pocket through reduced repair bills. Let's look at this whole action again in a smooth, uninterrupted motion. A unique feature of hydraulic buffers not true to mechanical systems is their soft buffer actions at low impact speeds to gently cushion the impacting load. This is because the orifice resistance to oil flow is much lower at slow speed. For example, in the case of this bridge crane trolley travel, the operator can drive down the buffer to maximum compression with minimal force, gaining additional operating travel. Let's take a closer look at some typical heavy industrial applications. In the steel mill transfer bay, this crane is loading steel billets weighing a total of 24 tons into a bed of 10 tons. 6 Type 4 Oleo buffers with a stroke of 114 mm can withstand a 1 foot free drop of the payload, taking 20 tons impact force per buffer. In this rolling mill, 8-ton red-hot billets emerge and strike the stopping plate at an average speed of 1,000 feet per minute. 4 Oleo Type 21 buffers with a 150 mm stroke gently stop the billets by exerting 20 tons of resistance per buffer. Watch the buffer action again and notice something. They are always fully stroked. This ensures a minimum deceleration force. Mining is another industry where safety is important. In the event of an overwind, this elevator cage weighing 70 tons and with a total weight of 140 tons could impact at a speed of 600 feet per minute. 3 Type 76 600 mm stroke Oleo buffers provide the necessary protection. Jack catchers literally catch the elevator cage after an overwind as it falls back. Type 4 114 mm stroke buffers absorb this shock. This steel mill 275-ton ladle crane has a total crane mass of 430 tons, travelling at 250 feet per minute. The Oleo Type 75 buffer with a 500 mm stroke gently copes with the impact forces at the end of the bridge travel. Oleo Type 9 400 mm stroke buffers handle end-stop impacts of the 275-ton ladle crane in the furnace bay. The heat and dust here are extreme, but Oleo buffers perform without a hitch. Here we have another slab lifting crane, and in this case they are using the trolley travel. The operator really puts this Oleo Type 21 200 mm stroke buffer to the test with this 64-ton trolley moving at high speed. Here we see the same crane with a total weight of 205 tons and moving at a bridge speed of 265 feet per minute. In this case, it will strike against another crane, both mounted with Oleo Type 9 400 mm stroke buffers. This is a typical harbour situation, and here we see a ship loader loading coal. It also makes use of Oleo buffers at its end stops. This car dumper mechanism is used for offloading coal cars at the end of the rail line. It has to perform under the most arduous of conditions and has 8 buffers fitted to it for protection at both ends of its rotational movement. We trust that this presentation has given you a clear understanding of both the principle of operation and the benefits of installing Oleo buffers. In conclusion, Let's take another look at these all-important benefits. The Oleo hydraulic dynamic performance means that you get a uniform deceleration. Robust construction means reliability and durability in the harshest of environments, withstanding high temperatures and dust. The efficiency of their energy absorption at over 95% means maximum structure protection. The recoil is provided by a gas spring, which makes for compact, clutter-free installation. Because they are designed for a long life, maintenance is reduced to a minimum. The fully damped recoil characteristic means that minimum energy is returned to the system. Because Oleo buffers are velocity sensitive, they always maximum stroke, thus ensuring a minimum deceleration force.